Okay. Um. Okay. Like I want to know how many of you are still outside of Taiwan. I think some of you are already in Taiwan, right? Uh, and having a quarantine. No. Okay, Maria's still outside. But when you are going to move to Taiwan, end of November or maybe middle of November, or Maria and Scarlett, end of November. Okay, so probably you will get into the university on December. Okay, so December, middle of December. Oh yeah. Okay. Oh yeah, Hans still outside, but you will come on which date, Hans? End of November as well. Okay. Okay, because I think on December, uh, we will have, or maybe middle November or maybe end of November, I will have uh, uh, PBL classes, problem-based learning classes or project-based learning classes, which means I will give some like a homework, but it's like a project, not like exercise, not like a regular practice that I usually give to you. But this will be like a project that you need to discover, find, and then if by the month of December you are still outside of Taiwan, then I will make it into like an assignment. Okay, because first at the first I want to make it in uh, like directly in a class. Okay, so let me write and get to you. Okay, so actually our class is PBL classes. So I will be given a project and then probably making a video, making a short video presentation about the project. Okay. Uh, the topic for the project is I'm still thinking, but probably for now the topic will be about topics. I will write in a general, uh, any mathematical uh, related topics. So what should you do? Because it's too general, right? So it's too general. But I hope you can find any real problem solution. Uh, yeah, I think this is the main topic. I will look for any reference that you can read or you can elaborate in the future. But I think for now, I will just giving you this first. Okay, um, you can check like many many website or at least on YouTube video uh, that have any project that related to the mathematics, or you can find something like how math can solve real world problem. I think this should be better. This should be better wordings for you to understand. So how math can solve a real world problem. So first, okay, you need to define the problem. It can be anything. It can be any problem. It can be related to finance, economics, and so on. It can be related to for example, programming, technology, or engineering. I think engineering is better for you because most of our curriculum is based on the engineering, right? Engineering problem. But any problem, it can be any problem. I will try to make or find any reference that is relevant for you. But for now, this will be the general topics for you. So define the problem, and then the second one is uh, math concept that's related to the problem, math concept, and then math application. Okay. So what you are doing is actually uh, find any article or reference, and then elaborate the article, elaborate, and explain in a video. And how the video should work is up to you, how you record, as long as you can make presentations about the whole thing here. That should be okay. So you will have a video and also maybe some like a report, okay, uh, and that will be so some of the percentage of your final exam will be based on this project. Okay, so that this should be helping you in at least to boost your score in my class. Okay, but I will give you in more details later. Okay, but at least you have something to find first. Okay, maybe you want to find uh, article or anything that related to mathematics. Okay, maybe next week or next 2 weeks I will be giving you more details and giving you some reference for you to look. uh yeah, I hope this will help you in mathematics. Okay, anyway, uh and any discussion first, any questions maybe related to this one, or you still confused on what to do for the project that I have mentioned? Okay, okay. So for now, you can, if you want to find like an article or maybe some YouTube video about, because I think there's a lot of YouTube channel that explaining mathematics, like some like how the concept can help you um, to build something or solve the problem, like how to predict like finance, the or even if you want to dig more and going into trends, like people now talking about cryptocurrency. Can you see any mathematical concept in cryptocurrency? Because cryptocurrency is actually using some mathematical concept, like the blockchain. The blockchain also, it's based on how you take notes and distribute the um, the informations, right? And also statistics also involved in that as well. And like in computer science, you have how to code, and it based on logics that is referred to mathematics as well. So there's a lot of topics, a lot of to cover. So you can elaborate as many as you want, but I hope you can find something that is special for you. Just one topic, not really going into everywhere, so you can have a more focused subject and discussion for you as well. Okay. Okay. For now, that will be the my idea for you. Okay. Next, I will maybe giving you some reference, but I hope you don't really, because if I give you reference, sometimes students will took that as the only one that they can study. Okay, so you can study in more like in more general. Okay, you can find anything that related to that topic. Okay. Okay, I hope it doesn't confuse you. Okay, so that will be the what we are going to do next. Okay, on PBL class, and I will give you details on what the class will be. Okay, because this is the project. The project should be at the end of the PBL, but the PBL itself is a class. So I will have break through some of our problem in the context of PBL, and then uh, let you. I will let you give more freedom in the classes. Okay, but I think that will be in the next, I think, 3 weeks. Yeah, 2 or 3 weeks later. Okay. So for now, we will just continue our classes. Okay, we are going to first looking back at the uh, last week feedback. Okay, so last week feedback, the question is asking domain of the function, right? Okay, first, if you look this rational function, okay, if we look at this rational function here, 1 over square root of x with power 4 minus 5x squared plus 4, uh, we are going to have something. So this is a uh, combination of this 1 and 2, right? So of course the domain will be a combination as well from 1 and 2. Okay. If you are looking at the square root, then we will have some x that is should be greater equal 0 to find the real solutions. Okay, because if x is less than 0, then it will be imaginary number, right? And if you have this 1 over something in the rational function, this should be x not equal 0. So a combination from these two will result in x should be greater 0. Okay. Now, to solve the problem and find in which number that we need to think carefully, we need to find the zeros first. We need to find the zeros, or the solution of x first. Okay. We find using some definition of a here. A is x squared. Then I can factorize. I have the number here. Then getting into the line number, and then check the sign. Okay. I want to have the sign that is positive. That is here, here, and here. Okay. It's all positive here. And that is precisely our answer. Okay. And all the number here, you should not equaling those number with the equation. So all the points were open interval. Okay, so this will be your domain. Okay, I think most of you got correct. Okay. Okay, the second question, you have this inequality. Okay, and you need to find the solutions. First, we can factorize the x cube. Okay, if you confused on how to factorize x cube, we can check using the syntactic divisions, checking 1, -1. Okay, and then we got that this should be -1. So we will have a factor of x plus 1 as a factor, right? Then we are going to use that, and using this as the other factor. And then by looking at this, okay, we will have two important things. Okay, the first thing is here, x should be equal 1, so that the result will be 0, right? If we have 1, then it will be 0 over something, right? So we need that x equal 1. But we also have x equal, not equal, it's not equal -1, because if x is -1, then it will be undefined, meaning this is actually an open interval. Okay, so we will have an open interval here and a closed interval that is x equal 1. Okay, and then we are checking our solutions. Okay, so our solution will be open interval from -infinity, -1, and including 1, closed interval, and then infinity. Okay, this will be our solutions. Okay, so that is why this is the answer. Okay, yeah, I think half of you, almost half is correct. Okay, all right. The next is we are going to move to chapter 4. And by the way, the first topic in chapter 3, that will be about the quadratic polynomial. Okay, quadratic polynomial. I think, yeah, that will be the topic in chapter 3. Yeah. And by the way, I have assigned the quiz for chapter 3. You are having, I think, until Saturday. Okay. Yes, polynomials. The quiz is polynomials. Okay. The quiz is polynomials. You have time until Saturday. Check your Google Classroom. Okay, check your Google Classroom. I will also announce in Moodle on about this quiz. Okay. Okay, now chapter 4. Okay, chapter 4. We will start with. Let me write chapter 4 here. Chapter 4. This will be about the exponent and logarithm. Oh yes, yes, Ardian. I will send the note today. Okay, after the class. Okay, so I will send the. I will upload this video and then send the note. Okay. Okay. Let me check. We will. Okay. So this will be. I think we can have some brief review about the exponential functions. Okay. Okay. Exponent. Let me write exponent. Okay. We called if we write exponential function, uh, this number 2 here, we call this is our base. Okay. For example, to understand these functions, if we have check if we check x, okay, from 1, x equal 3, x equal 10, or even x equal maybe large number 30, we are going to look at f1 is 2, right? f3 is 2 with power of 3, it's 8. F of 10, this is this, right? And f30 is something big, right? Looking at this, okay, from 1 to 8 is probably not really that big, but from 8 to 1000, the difference is 3 to 10. So 3, 4, 5, 6, 7, and until 10. The difference in the exponent here is just a 7 number, right? Just 7 unit, 3 to 10. But the results is really significantly increasing, right? So the idea is the value increasing very fast. So even a small change in variable can cause a dramatic change. Okay. Let me move this graph first. So I will explain first about the exponent. Okay. Okay. If I have some a with variable x like this, okay, this expression, this will be. I think we have some definition at the early beginning of classes, last month, I think. When we have this, then we have this is positive, and x is a rational number. But what if, okay, what if x is irrational? So again, we are a little bit fast flashback to irrational. Okay, I've given you the definition: irrational and rational, right? So irrational means uh, the form is decimals that have no um, no fractions form. Okay, so you cannot make it into a fraction. For example, okay, if you have just 0.5, you know that this is 1/2, right? We can have this, but sometimes, like for example, the square root of 3. If you check with your calculator, it will be having, and notice that I wrote this as an approximation. Okay, if you remember the calculus thing, that this is one of the example approximation. So this will be 1.73205, and then still continue, and then we cannot really define this in a fractions. This decimals, okay, and we call this a irrational number. So this will be irrational number. So if we have base of 5, and then we have square root of 3 like that in our exponent, we can approximate this with some decimals. Okay, for example, if we use this, or if we are using up to several digits as well, it will result in better approximation here. So at least, okay, at least uh, we can prove that from here the law of exponent are still true when the exponent are real number. Okay, this is just to show you that if we are going to uh, involve the irrational number, it still can be true for our case of exponent here. Okay, if we are going to involve the irrational number. Okay, so we are arrived at our definition of exponential function. So exponential functions is defined. Let me write exponential function with base a defined is defined for all real numbers x, okay, where a is positive and a is not equal 1. Okay, I think the example is easy for you. If you have 3 with power of x for x and changing the basis, and it will also change the graph, right? Okay, now the graph, okay, if you look here, okay, uh, we have two graphs, okay. The first is the red one here with a base of 3, okay, and the other, the blue one here, is let me use the other blue, is 1/3 the base, okay. um, we can also think this as, okay, if we have this y equal 3 with power of x, the other one is we can also think as 3 with the power of -1 and then x, or we can have 3 with power of -x. Or, okay, in case of transformations, okay, if you remember how to transform, if we are going uh, to reflect, okay, to reflect reflecting about the y-axis, then actually you change the the x becomes -x. That is reflections about the y-axis. Okay. Okay. And now, if we are going to take another examples in the other bases as well, we can see also looking at this. Okay. So looking at this 2 with power of x. Okay. 3 with power of x, 5, 10. You will notice the difference is when you have 2, you are okay, you are here, okay, it's going up, and when you have 3, it's going faster, right? It's going faster. You have seen the gap here, right? This is the gap. Yeah, this is the gap. And you have 10 is also faster. You see the gap here, right? It's increasing, the value is increasing faster, and you see the 10 also faster here, okay. And you have the reflection as well, okay, 1/10, 1/5, 1/3, 1/2. This is 2 -x, 3 -x, 5 -x, 10 -x, okay. And you will see other important as well is this x-axis. The x-axis is our horizontal asymptote, okay, because the result will be never negative, right? Never negative from here, unless you are, if you have this negative here, then it will be reflecting through x-axis, right? But if not, then our x-axis here will be our horizontal asymptote. Okay, because if we have, this is 0 as x going to infinity, and also x going to positive infinity, okay. So you will have domain for x is all real number, and range, how about the range? Is from 0 to infinite. Okay. Okay, we can simply say that, okay, this is just the summary for the graph of exponent. So y equals 0, or the x-axis, will be the horizontal asymptote. It has domain of all real number, and range is from 0 to infinite. Okay, and you will have this. Actually, if you maybe not really focusing on this a property here, you can always remember that if you have like this, it's the basic one. It can be a with power of x, and you have this, which is the reflections of a with power of x. You can remember that this should be a. The a will be from maybe from 0 to 1. Okay, so if you have this 2 with power of x, this will be having 2 with power of negative x, or half with power of x. Okay, anyway you prefer. Okay, if you maybe difficult to notice that this a, difficult to notice the a here. Okay, you can also say this is this. Okay, if you want, okay. Okay, now okay, yeah. Okay, if you look at this tree graph here, we have our transformations. Okay, so the blue one is the original functions with base some number. We are using the 2 with power of x here. If we plus with 1 here, 1 plus 2 with power of x, which means what we are going to do here is we are going to move upwards. Okay, we move upwards 1 unit, right? We move upwards 1 unit. But you are going to notice that there is a slightly change in the gap, right? So that is because we are going to notice that at first, at x equals 0, okay, let's check at x equals 0, our y will be 2 with power, this is 1, right? But when we have another transformations, this will be 2. That is here. And if we check the other case as well, here we have 1, and then 2 with power of 1 is 2. But if you plus 1, then it will be 3. So it will be here. It will be 3. And same thing if you have, this is 2. This should be 4. And it should be having maybe 5 here. And this is 5, and then and so on, and then so forth. Okay. So the gap here will actually going to at least meet up. Okay. And when, do you know why the results seems that it's not really having same proportion here? Because 2 with power of x is going really fast. Okay? It's quickly increasing in value, right? Really fast. It's grow really fast, right? Compare with just plus one. Okay. For example, for instance, okay, for instance, if you imagine from two, okay, plus one, and then two with power of two plus one, two with power of three plus one, and imagine you have two with power of 10 plus one. Here you are just okay. We still have 3, 5, which is we can observe and see the difference, and it will see. It seems it's still similar. Okay, the graph, and then you have 8 plus 1, 9, all still one digit, right? All still one digit. But then if you have 2 with power of 10, it's 1, 2, 5. It's now it's thousands. Okay, that's why the distance looks like this. Okay, the distance looks like this, really having a gap like that. Okay, I hope you get my idea of the exponent. Okay, if you are because sometimes, okay, when you learn in the class, learn mathematics without really realizing the graph, how the visuals is, sometimes you will get blur. Okay, you have confusions on how you are actually analyze functions, analyze any formula in math. Okay, let's check another graph. Okay, now this is what I've told you before. So if you're reflecting about x-axis, okay. So if you want to reflect about x-axis, then you need to make its y negative. So first, okay, this is the base. Okay, this is the basic function, 2 with power of x. What you're going to do is take the negative of that y. So negative, and then this is the functions. So if this is f of x, then this g, if I make it g, this will be negative of f of x. Okay, it's different from the previous cases when you have the reflecting about y-axis. This will be, let's say we have g of x. This is f and then negative x. Okay, I hope you still remember about the transformations. Okay, because in all types of functions, if you are using the transformations, then actually all the principles the same. Okay? It's the same thing. Okay. Okay. Another cases here is if you have this x minus 1 here. Okay, what does it mean? If you look here, the blue one is the original, right? The blue one is the original. And what you are going to do is actually you are moving this 1 unit, right? 1 unit to the right. Okay, so if you plus like the first one here, it moving 1 unit upward. But here, 1 unit to the right, x minus 1. Okay, so if you have x plus 1, this will be 1 unit to the left. Okay, so let's see what's the whole thing here. Let's see the graph. Okay, let's start with here at x equals 0. This will be resulting 1. 2 with power of 0 is 1. Okay, it's clearly show that as well here. And the other case, when you have x minus 1, this will be having 2 with power of negative 1, which is half. Okay, it's half. So I think it's clearly also showing you this the idea as well. Okay, that is the half. Okay, this is 1/2 here, and then we are moving to x equal 1 here. Okay, when you have just the original one, you have 2, right? 2 with power of x. 2 with power of 1 is 2, but 2 with power of 1 minus 1, it's 0, so it will be 1. So it should be here. Okay, so that should be giving you the idea that the graph is moving 1 unit to the right. Okay, but it seems that if you look closely, the gap also changing, and it seems that if you see the first, the gap is getting narrow as you move to the right, and here the graph is getting widened. It's getting bigger, right? Okay, so it should be giving you some idea on how you should do in the graph. Okay, so when you need to draw a rough sketch to get you some idea about the functions, like maybe you solve some problem, but you need to know first how the graphs looks like. This is how you can do. Okay, you can imagine when you have like maybe what will be if we have a 3 with power of x, and then you are thinking, okay, how about I need to have 3, and then I need to take it somewhere 4 to the left, and then maybe plus with 4 also. So you move to the left 4 and then upwards 4. Okay, 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 at least you get the idea of transformations. Okay, idea of transformations. um there is actually compound on an interest. Okay, let me just give you the general formula. Okay, so we have compound and interest. Okay, so this is also applications of this exponent. Okay, so you have a functions that is defined by this. So what is a? A is the total money or amount of money after t years. Okay, and then p is principal, r is interest rate per year, and then n is number of times interest is compounded per year, and then t is number of years. Okay, okay, let me give you an example, okay, on how we are going to use this. Okay, a sum of $1,000 invested at interest rate of 12% per year. I think that's quite high, right? Find amounts in the account after 3 years if interest is compounded annually, semi-annually, quarterly, monthly, daily. Okay, so you have several examples here. So first, okay, we are going to have an annual. What annual means? N will be equal 1. Okay, so annual will be 1 year, compound one time, right? So we have, let me write the formula, a TP1 plus R divided by N, and this will be NT. Move here a little bit, and we are going to see that the principal is 1,000. The first money that the person invested, and then the R, the rate will be 0.12%, right? 12%, so 0.12. And how many years? It would be 3 years. Okay, 3 years. Okay, so if we compound annually, so compounding, so this will be the compounding. So compounding will be the n. Okay, so we are going to see the formula will be 1,000, 1 plus the rate 0.12, and n is just 1. Okay, and this will be 3, and this will be resulting 1404.93. So if we are just compounding only one time annually, okay, that will be our total money. If we have semi-annual, what semi-annual means is 1 year, on 1 year you have 2 times compounding. Okay, 2 times compounding. So n is equal to. So using n equal to, this is 2, and then 2 and 3. Okay. This will be resulting 141852. Okay. And if you have a quarter, you have 4 times. Okay, in 1 year you have 4 times quarter. 4, and notice how the numbers is changing. Okay, it's also get increased. And if you have monthly, so every month, so which means there's 12 months, right? So this will be equal to 1430.77. So if you have daily, then 365 days, right? You have 1 plus. And it seems that it's also increasing, but look at the change here. Okay. If you are looking at this, okay, this case here, if you are looking at if this is n is equal to 65, right? Imagine when the n is getting bigger, how will be the results? Okay, and that's is actually uh, our definitions later. Okay, but if you are going to increase, what will be? If you have a calculator, you can check how the change will be. Okay. Uh, so at least, okay, from here, um, I can have 1 plus 1 over something with power of n. I can rewrite this statement as this functions. Okay. And in fact, from this compound of interest, you can also find a definitions, okay, which we are going to uncover in the next page. Okay, but let me give you this as a note first. Okay. 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 The definition of E, okay, actually we can also use from that compound of interest. So when you have this expressions and you increase as n is larger, okay, the results, okay, of the result will be getting closer to some number that is actually this. And we know that this number is actually our Euler number, or E. And this idea is more precise in calculus. Okay, if you remember the concept of limit, then if you have limit as n approaching infinity, this is precisely E. But E itself, okay, E itself, if you see here, okay, uh, actually you can write E like as long as you want, 1828, 1828, 4590, 4523536, and still going on. I'm not sure um, the last uh, the last findings on how many decimals in E, because actually mathematicians they want to find how many numbers, or what numbers are here, and can we make also another discovery from these decimals? Okay, is there any pattern? Is there anything that really interesting behind this? It's still going on. It's still going on. So E is a rational number. We cannot make it into fraction, or we cannot write its exact value in decimals. because it seems the decimals, it won't stop. It's going on, having a number behind, and I don't know how many numbers that your computer can compute. Okay, or your calculator can compute. Okay, of course your calculator has limit um, its brain, right, in the processing. Yeah, and like the computer, or maybe using the supercomputer, uh, like they have like a superconductor inside. I think it still have some limitation, and then cannot write exact form of the e, okay, as a value. Okay, if we look at this e in a graph, okay, if we are using e as our basis, okay, so this is base, our base is e. We call this a natural exponential function. The base is e, but oftenly we call it's simply called the exponential. Okay. So the exponential function itself, sometimes it refers to the e with power of x. We can just say that as our exponential. Okay. And I think the rest is pretty similar with the previous exponent, but we are just focusing on, we are having a new base called e. Okay. So if you have like this is e, I think this is bad. Yeah, I think that way. And when you have the other way around here, this will be the e with power of negative x. This will be e with power x. And the rest, like transformations, using e in compound interest, that will be similar. Okay, so you can also use the compound interest as b, e, and then this is, so you are changing the inside uh, compound of interest. So this is same. Okay, a is the amount. Okay, p is the principal. The basis money you invested. Okay, r is interest rate. T is years. So you can change the whole compound interest formula with e. This is we called uh, continue continuously compound interest. Why we call this as continuously compound interest? Because it will continue as n is increasing, like the previous formula n. As n is going to increase and getting closer to infinity, then it will reach a special number e. Okay, that's the case, and we can simply use e to note that this amount is the continuously compound interest. Okay, we can, I think we can move on to other sections. So exponent, Euler number, definition of e. Okay, I think I have also mentioned in the calculus class. Okay, but this is just to a brief review and with some visuals. Okay, and other application as well. Okay, any questions first? Any questions? Okay. Okay, let me go to uh, logarithmic functions. Okay. Okay, before we are going to logarithmic functions, let's see this exponent, okay, with base of a with power of x. If we look here, and we take this as our task, okay, this is horizontal line task. Okay, if we look here and we observe, okay, that there is exactly just one, okay, just one point in every horizontal line task. That means that a with power of x is one-to-one functions, which means we can have the inverse. Okay, so from this inverse, we will have a definitions. Okay, we will have a definitions. Okay. So let uh, f inverse of x equal y. Then our f with power with y, f of y is actually equal x. And then let a be a positive number. Then the logarithmic function with base a, we are using in the log, and then a, that is how we write in logarithm, is defined by log a x is equal y, or in exponent we can write this as a with power of y equal x. Okay. And precisely these two functions here are inverses each other. Okay. If you look at this a with power of x here, and we are reflecting the functions which about the y equal x. Okay, that is the definition of uh, f inverse. Okay, so f inverse can be obtained by reflecting about y equal x, and you will see from this graph as well. So the logarithmic here is practically the inverse of the exponent. Okay, okay, let me give you time to write. Okay, so we can also write. Okay, we can also write if we have f of x is a with power of x, then we will have f inverse. Okay, this will be resulting. Let me write a little bit to the left. The f inverse will be log a x. And if we have f, and then this will be f inverse x, this should be x, right? That means we can write this a, and then log a x, this is x. We can also think this way, okay? So instead of, I know, okay, some years you learn logarithm in high school probably, and you know some law of logarithm, right? How log can be manipulated uh, with certain things, and actually, if you know log and exponent is basically from the same root, you can have some definitions based on uh, that connections. Okay, so f and f inverse. If you have the exponent, you can have the inverse is log, and if you have log, then the inverse will be the exponent. Okay. Okay. Uh, the second thing here is the graph. Okay, how to graph the log. Now, if you're going to see here, okay, um, we have base 2. Okay, so what log will do in our graph is uh, x is 2 with power of 3 here, but we are going to have the log, only the log. Okay? What that means is we are only focused on the power, okay, the power or the exponent. So log base 2 of x, it will be 3, okay, from 2 with power of 3. So we are just taking 3, taking 2, taking 1, taking 0, and then making it into negative form. And you'll see that it's going to have that kind of graph. Okay? And there will be an asymptote, right, at this point here. Asymptote. Okay. If you remember the exponent, the asymptote is on the x-axis, right? Yeah, probably. Yeah, if you have uh, the mirror reflecting through the y equal x. Yeah, probably. Yeah, like that. Okay, you see the inverse from these two. Okay, let me just take it. Oh, okay, so that will be our log. So a little bit property. If you have log a and 1, that it should be 0, right? And if you have log a of a like that, that should be 1. So how we should taking it into our consideration. So the base a will be our focus, okay? And what need to be raised? What is the exponent that when you have this, it's equal 1? So this should be 0. Okay, that's why it's 0. From this case, what should be a increase with something, but it should be the total will be just a. So this will be 1. Okay. And if you have log a and a with power of x, then this should be x. Okay. So that's why uh, a log a x, this is x. Okay, so this is just basic property of the log. Okay. Uh, okay, I will continue. Some idea on graph. Okay. Um, if you see from here, you are noticing something interesting. That is all the graph with different base 2, 3, 5, 10. They will all be connected and have one intersection here at x equal 1. Right? And precisely, all this log is the inverses of um, 2 with power of x, 3 with power of x, 5 with power of x, 10 with power of x. And at x equal 1, what is really happening there? When you have log 2, 1, this should be 2. This should be 2. Need to be raised in power something number that equal 1. So this should be uh, 0, right? So log, any log with any base that is actually when x equal 1, this will be 0. Okay. Because when you have other number as well, it has the same, for example, 5, then this should be going to have 5. This is also need to be 0 to get 1. That's why at x equal 1, all will have an intersections. And the difference with the exponent, but I think similar, but the difference is just at exponent, you will get as x getting infinity, the f of x also getting infinity faster. Okay, but here as x getting to 0, closer to 0, the f of x is getting to negative infinity. And here is x getting in negative infinity. F of x is getting closer to 0. Okay. Now the transformations. Okay. I think it's pretty much similar with the exponent, but it's just the inverse. Okay. But the idea will be the same. Okay. So you have the blue, the original functions, log with base of 5 of x, and then you plus 2 and make it into g. Then you will have from this one here, you will have here plus 2. So this is number 1 is the easy way to see the gap because log with any base of 1 will be 0. So just plus 2. So it will be increasing 2 units, right? 2 units. and I think this is the same. Okay. And when you have this x minus 3, okay, if you look at the basis function, it's here. That is taking, so it need to have x equal 1 to get the functions get into 0, right? So similar idea with this function h. When you want this to be 0, then this log 10. So if you want this to be 0, then x minus 3 should be equal to 1, which means x should be 4. Okay. And when you look at that, this should be having 3 units gap. Okay. So x minus 3 means going to the right 3 units. Okay. That's a little bit of transformations. And same thing if you have, if you, for example, if you have log to x and let's say Rx is negative, okay, which means you are reflecting about x-axis, right? Let's see here. For example, that should be that. So reflecting about y, yeah, y-axis. Okay, another thing is okay, before this, let me go through the common logarithm. Oh, wait. I think, oh, sorry. I think this should be, this graph should be, sorry. This should be log to negative x. The other one should be, if you have this, then it should be have this. Okay. This will be f of x. Okay. Yeah, okay. This is reflecting through about x-axis. Okay. Okay. Okay, common logarithm. Logarithm with base 10. This is called the common logarithm. So if we wrote down log and then x, this means this is log with base of 10x. So if we have log 10, then this is 1. So we have log 100, this is 2, because this is actually from this. And if you have log 1000, this will be 3 from 10 with power of 3. And I think there are several applications on this log with physics, especially for sounds, for measuring the decibels for sound, audible sound. You're using the log, right? Why using the log? Because, for example, if you have this log with base 10, okay, if you have the data set, the data that is increasing really fast, like from 10, 100, 1000, and it's best to move it or to change it into log. So if you read the scale, you can observe in details, and you will see when the graph is changing, when you have the significant data, okay. And then it will be easier if you are using the log scale. Okay. That is common logarithm. The next thing is the natural logarithm. So this is just log with base e. We are writing as ln. This is log e x. Okay. And remember that if we have y is ln x, then this is e with power of y equal x. And the property is still same as the previous cases. So if you have ln 1, this is 0. ln e, this is 1. Okay, ln e with power of x, this is x. And then e with power of ln x, this will be x. Okay. The reason is the same as previously mentioned. And I think this skill in logarithm is useful, especially when you are doing the calculus things. Sometimes it's make your life easier. Okay, I think we can have I think just one more section, and then we can have our class finished today. Okay. Okay, so we know that from property that if we have log with base of a, and then we have a with power of x, this will be x, right? Okay, let log with base of a, and then the whole thing, the result a is equal to, let's just make it u, okay, and then log with base of a, and then the other one is b, it's v, okay. So this will be a with power of u, this will be equal a. This a with power of v, this will be equal to b, okay. Then if we have log base of a, and we need to multiply both of this, a, b. Log a, and then a power of u, a with power of v. This will be log a, and then this will be a u plus phi. And we can simply say that this is u plus phi. This is log a log base of a b. And then another, if we have let the log a is u, then a u is a, right? Then a log a, if we have any constant c with here, okay, then this will be log base of a. This will be a with power of u, and then with power of c. And this is equal log a, and this is precisely u c, or c log u a. So we have at least 3 property. So this is also can be done with the oh, one more, sorry, I forget this second one, sorry. So the second one is here, the same with the first one. So log a, and then you have a over b. This will have resulting a u a phi like that, and then log base of a, and you know that this is u minus phi. I think it's not correct here. Okay, and this is precisely u minus phi, or log base of a minus log a, like that. Okay. Right? Okay, now this altered expression I will write in the simple words. This is basic of law of logarithm. Basic principles. First is log base of a, ab. Then this will be log second log a, and third, if you have log so basically this is saying that you can move this to the front here. Okay, that's why the calculus part on log, we can have that as well to solve some of complicated problems. So, example, if you have log, let's say 4, 2 plus log 4, 32, this will be log 4, 64. Or we can say that this is 3. Or you can start from here and then make it 4 with power of something, 4 with power of something, if you want. Okay. Okay. Oh, and then for this part here, okay, for this number 3 here, if you have log, for example, 2x and then cube, this is not the same as this. Okay, this is wrong. Okay, this is wrong. So this is not equal. Okay, this means, okay, this means you have log, okay, but if you have log 2 and then x squared, and this is, you can write 2 log 2x. Okay, and also this means that if you have log a plus b, this is not the same as this. Sometimes this is the common mistake for students, so this is not okay. Okay, I will stop here. Any questions first? Okay. I think we can still have a little bit. Yeah, I think just one more. I think that should be okay. Okay. Yeah, I think one more a little bit sections. Okay, let the y is equal log with base of b x. Okay, we know that this is the exponent form. Okay. Okay, let's look at this first. Okay, let's take a look from here, from this exponent. Okay, so let me write here b with power of y and then equal x. Okay, we add log, okay, with any base. Okay, let's say base of a. Let's say that that's base of a, and then we are going to change the expressions. This will be y log of a b equal log with base a of x, and we get the expression that y is log a x divided by log a b. So our log bx at the beginning, we can conclude that our log bx is log a x log a b. This is we call a change of base. So you have something here. You can actually make it in any base here. You can have base 10, for example. You can simply write log bx. Just write log b. This is still okay. It's still okay. It's base 10. It's still okay because a can be any base, any number. So we call this change of base formula. Or if you want to look into if you have log b a, we can also write this 1 log a b. Okay, because log b a log a log a b, so it's become 1 over log A. Yeah, or you can write it as log A over log B, and then you can think 1 over log A log B, uh, log B A, and then you can have 1 over log A B. Sorry. Yeah, you can think this way, or you can have this way. Same results as well. So we call that a change of base formula. I will review a little bit tomorrow for some maybe practice and exercise in terms of a log. And of course, I will not start with something that is pretty obvious, like uh, just uh, maybe like log 920. This is log 20, log 9, blah blah blah. That's too simple. Okay, I will start with a little bit complex problem to help you to exercise and help you in also doing some later also in the calculus. Okay. Okay, if there is no questions, I will start with the feedback time now. So I will stop the presentation. Okay, please join in. I think I've just prepared quick questions just to look at the picture and then just select which one is the correct answer. Okay, let's start the quiz. Okay, have you joined? Okay. Okay, let's start anyway. Okay. Okay, 7 students. Is it correct? 7 students. Should be 8, right? Okay, anyway. Okay, let's start. 3, 2, 1. Yeah, just choose which one is correct. Okay, 5 seconds. 5 seconds. Yeah, all right. Okay. Okay, be careful. Okay, be careful. You can check actually the answer if you check x equals 0. Okay, next questions. Okay, good. Okay, next question. Okay, 4 options you can think. I hope that's enough for the time. Okay, good. Okay, next question. Okay, get ready for the next one. 3, 2, 1. Okay. Okay, I hope the graph is looking good at your phone. Okay. You need to match the functions a to d with the graph 1 to 4. Okay, 50 seconds. Okay. Okay. Think, yeah, you did good. Ah, okay. Okay, who's this? Okay, so congratulations. Okay, so yeah, if you are not having any questions, then we are finished. Okay, so the class is finished, and see you tomorrow. Um, if you have any questions, please let me know. Okay. If you have anything to discuss with, okay, if you have any questions, you can ask me. PDF of the pre-calculus book. I do have the PDF, but I don't think I can share it with you. So yeah, and I don't think all the chapters in the book will be necessary important. I will just took some of the important points on the book for you. So I already summarized in the lecture. So do you have any other question? Okay, if not, then we can um, finish the class. Yeah, the class is finished. So you can leave the Google